Okay, so everyone, welcome. We are having a Space Center seminar today, and we are very pleased to have Säm Krucker from FHNW near Zurich, and he will talk about solar flares X-ray observation with CubeSat. He's been doing solar physics in his career, and he's been doing a lot of instrumentation development, and in particular the X-ray imaging spectrometer STIX, which is on board of the ESA Solar Orbiter mission. And it will tell us about science and development of these instrumentation. So welcome, Säm. When you're ready, you can start.
Okay, welcome everybody. I'm gonna do a little bit of mix of science and instrumentation. I hope it covers the interest of most of us, and we'll see. I grew up in Switzerland and did my PhD at ETH, and then moved to Berkeley and learned most of how to manage space programs there, and then got this opportunity to come back to Switzerland to do this instrument for ESA called STIX, and of course I'm gonna introduce that too. I will start with the sun of today, if I can move my thing here. This is downloaded from the internet. This is observations from the last 2 days. I think it's 1 day delayed. It's not today, but the previous days. This is the sun in EUV, and you see it's animated. You see that the sun rotates, and what we see here is UV emission, and where it's bright, that's where there's a lot of plasma at 1,000,000 degree. We see a lot of fine structure, and we see a lot of emissions from different regions. There's also dark spots. These are so-called coronal holes where there's not so much plasma there. That's why they appear dark. We see a lot of time evolution and a lot of small structures. And this is all related to the magnetic field and the activity of the magnetic field on the sun. And if I go to the next slide, it compares just one frame to the left that we saw before in EUV with an optical image. And we see there's a very prominent sunspot near the eastern limb. That's over here, and another one there. And we see indeed that's also the place where it's quite bright in EUV. Same over here. So there's a clear correlation with where we see this hot plasma, where the magnetic field is strong. There's another way when you make these observations in the optical range. Generally what is done, it's observed around a line emission, and then you can derive how this line is deformed. You can derive what is the magnetic field strength. And then you can make this type of maps of the sun where black and white are strong magnetic fields, and black, I think, means the magnetic fields is directed towards the sun, and white coming out. And gray means not that much, not that strong magnetic fields, or they're averaged out within the pixel size. And now we can see really a good, clear correlation that this is a region with a lot of magnetic field. That's the one we saw with the big sunspot. Over here, this is this part, and then this patch over here. There is a region of strong magnetic fields here, positive, negative, and indeed that creates this little thing. So all this hot part of the solar atmosphere is driven by release of magnetic energy. So the sun inside creates, is turbulent, and it's hot gas. It creates magnetic fields. These magnetic fields can leave the sun And then in the solar atmosphere, part of that energy is converted into kinetic energy, and that makes this hot plasma. And so in solar flare physics, we study this effect. How is this energy converted from the magnetic field to the kinetic energy? And X-ray observations are an excellent tool to study that. And I want to introduce that in the next few slides. This is one other way to roughly and quickly see what is the current activity on the sun. And these are time profiles here over the last 6 days or so of the total integrated X-ray flux of the sun. There are 2 lines shown, and they're just a slightly different energy in the X-rays. And with this curves, we clearly see when we have very strong eruptions. This is a log plot, so that means when we see something what happened this morning, suddenly the soft X-ray flux goes up by 1, 2, 3, almost 4 orders of magnitude. So these are these very biggest eruptions, the biggest flares that heat some part of the sun quite efficiently, and then it radiates like crazy in X-rays. And so these 2 flares that we see, and these are categorized according to these numbers. So our favorites are the X-class flares, the biggest. They came from that region with that very strong sunspot. So this is, again, this very clear correlation. The solar activity has a cycle. So it's not that it always looks the same, but there's an 11-year cycle, or more or less a 22-year cycle. But every 11 years, we reach a maximum of this magnetic activity. And currently, we are very close to that. And so this is an old graph that showed the magnetic field observations, again, with plus minus over a solar cycle. And we see 97, for example, was solar minimum, and not many. And these are the equivalent soft X-ray images that are associated with it. And then, as always, this is the plot. I show always this plot of the solar cycles and the activities, and there is also the prediction on it. This is the solid white line, and I think this is really a recent prediction, and we see we are really climbing up, and the predicted peak of the 25th cycle that we are in now is just around the corner. So we have really the most exciting 2 years in front of us for solar flare research. And then I put in that green arrow, that is when our mission Solar Orbiter was launched. And you see that really nicely covers that one solar cycle. Here are a few more images of specific eruptions. This is a composite of several of these EUV images. Then you get several aspects of these lines are sensitive to different temperatures. And so what we see here is a combination of 1 million degree hot lines and maybe 3-4 million degrees. And what we see is that an eruption really has a center where it starts. If you look careful enough, you see there is indeed a shock wave moving out. And all the black stuff, this is actually not so hot plasma that is thrown out. And because it's cold and rather dense, it blocks the emission. So, or absorbs the emission from behind, and that's why it appears as black. And you see, sometimes these eruptions, clearly that it will leave the sun, but part of it will also fall back, this black sense. This is going one step further. This is now with not only observation from looking at the sun, but the green observations are done by covering up the sun and then look at scattered light that is seen. And because what is ejected is higher density than what was there before, the emission increases in the scattered light. That's what we see here. So with this, we can then follow the eruption from the sun near the surface where really the energy is released, how it moves out and away from the sun. And again, we see some of the plasma falls back to the sun. So it's not that all of the plasma always escapes. And there are also some eruptions that fail to eruption, as we say. This is when the magnetic field above the eruption is really strong, then it just bounces off and it cannot get out. Then the next step, this is another type of instrument that's not anymore a coronagraph, but it is simply an optical instrument that looks to the side. This is not a blue. And again, what we see is scattered light from the eruption. And of course, in addition, you start to see the stars as a background emission. And so with Solar Orbiter, the idea of the mission is to fly away from Earth, get closer to get a better look, but also really to fly through this such eruptions and make direct in situ measurements of that. And here, a very short animation. This is now not data. All before was data. This is just animated to show what happens when such a cloud would come towards Earth and hits the Earth's magnetic field. So these purple lines are the magnetic fields. And you see Earth is well protected from these eruptions. But nevertheless, it can have effects. And of course, the regions that are least protected are the polar regions. And we saw in this animation that some of this Earth's magnetic field that protects us can get also reconnected and change shape. And then it has influence on the polar regions. And that's then the region where really particles from the eruption can also enter and can maybe also get re-accelerated. And this is then the origin of the Northern Lights. So we have really this system of the sun with its magnetic field, it erupts, and if the eruption can come towards Earth, we get a direct effect. And so it's not that the space between Earth and sun is empty, but we have really this, the sun is really filling the space between sun and Earth with this erupting plasma and magnetic fields. And this is then what is called space weather, as we have a permanent change in that. And to predict that space weather is of interest because this has also influence on us living on Earth, but mainly on all the space missions that we have out there. This is a nice animation that shows this in a log plot in radial distance. This is done by Greg DeForest, just to show this whole system, how the sun throws out this plasma and the magnetic fields and how this moves out. What I didn't mention is it's not only the eruption that happens, but we have also a more steady flow of gas that comes out, and that's the solar wind. And so Solar Orbiter is now flying in this to make combined measurements with 10 different instruments. And so this is a cut through Solar Orbiter and with all the instruments labeled. It's more to show not the individual instrument, just the amount of instruments that we have, right? So this is what each instrument team had to compromise. We got limited mass, limited power to do this. But for that, we have then a maximum of possible instruments on board that jointly measure the space weather and what the sun does. And so this is a sketch of our instrument. This is called STIX. The S is for spectrometer, the X obviously for X-rays. So it means we measure the spectrum in X-rays, but we also do imaging. So that's the I in there. Today, the imaging in X-rays is a little tricky thing because it's not so easy to bend X-rays. And so we use an indirect imaging system, but I will not really go into details of that. And of course, with all these instruments, it's a big collaboration that we do. It's not just one place. The lead was at the University of Applied Sciences, Northwestern Switzerland, but of course, we had a lot of partners, science partners, but also hardware partners. And one major team was Almatech just a few houses down. That helped us build that. And then finally, we started planning on this. The first concept study was 2001. And then in August 2017, ESA mounted it on the spacecraft panel. So this is STIX, the instrument that flies. What you see there, that's the spacecraft panel. Yeah. These are the STIX detectors. So these are detectors that make measurements in X-rays. We have 32 of those on there. So the X-rays come in, hits this shiny surface here. This is a crystal cadmium telluride, something similar as silicon, but it works better for the higher energy X-rays. And so this is our set of detectors. And we have many, many spares of these detectors. And that's one reason why I was here. How would we want to fly those spare detectors on a CubeSat? This is me. I always like to show that, and it's also an announcement. I always like to look at this because I was so relieved when we were ready to ship. It was just before we packed it up to actually drive it from Switzerland to the UK by a private car. So I should have maybe add one picture here when we were at Le Havre to go on the ferry. We, of course, naively went to where the passengers go, but we should not go there because we needed the stand for our instrument. So we had to go where the trucks go. Oh. And it's pretty funny to be there behind the trucks with your little private car. And actually, you can't talk to the guy because those guys are high up so that they can talk to the guys up in the trucks. So all kind of good stories. And this is Solar Orbiter, just to get you an idea how small it is or big it is. It's doing thermal vacuum testing in Munich. And then we had a launch in 2020, just before the COVID arrived. Though it was actually already arrived, but we didn't know about it. And so this is the orbit that we are in. And I often say we when I talk about Solar Orbiter, and I know it's not a we. So Earth here, Venus, Mercury, and the Sun. So I let this play. I think this is the next. So the thing to get in closer, you can use gravity assists from the planets. So you give some momentum to Venus in this case here, and then get thrown in a little bit closer. So we did Venus gravity assists, and then back to Earth, another Earth gravity assist. And then this was the start of the nominal mission with the first perihelia. And we go in roughly at 0.3 AU. So the 3 times closer than Earth. And of course, you go out again. And so this movie will play until today. I think it's one more turn, maybe. I don't see yeah, so it's here. So this is where Solar Orbiter is at the moment. So it's actually intersecting the Venus orbit, but Venus is not there. So not every time, but this is in phase. Every third time or so we do a gravity assist. And so this is where we are now, and now we're going in closer, and it's solar maximum. So this is maybe possibly the most exciting next 2 months to do that. And this is our treasure. This is an overview plot of all the STIX flares that have been observed since 2021. It's about 45,000 individual flares. Of course, in this plot, you don't really see individual ones, but they're all a little bit grouped together. But nevertheless, you see we launched at the right time for STIX. Activity was rather low the first half year, but now it's high activity. And you see the background that you see there that is decaying. This is the radioactive source that we use for calibration. Mm-hmm. And so it's a radioactive source, so it decays. It has a half-lifetime of 10 years. And so we are 3 years in, and now you start to see we get a little bit of lower background. And so this is really a great data set. I mean, I'm more, if it dies tomorrow, I'm still think this is a total success for me. all the work that I put in for to get this back from the science. This is great. To give a rough indication what it actually means to get in closer. So it started at 1 AU, and this is actually real data. And you see that what it means to go to 0.3 AU, it gets bigger, yes, because it gets closer. So that just does a thing. The other thing is, of course, being in close, you get really fast. And so the most fun part is the shortest. Very close. And then the thing we should never forget is the biggest handicap for a mission that goes away from Earth is that the telemetry is limited because it's so far away. And the antenna, this is the antenna doing a test when they lift up the antenna to simulate how they can move the antenna. But you see how small the antenna is, and you are so far away, right? Sometimes orbiter is behind the sun, so light travel time is 15 minutes. And you communicate through this 1 meter antenna. And so that's why the price we pay is that the instrument that could take 1,000 times more data, but we cannot send it back. So that's a limitation. That's why for most instruments, they're not on all the time, but in campaign modes. And then even in a campaign mode, it's only for some, with these nice images, that's only taken then for a few hours a day. This is possibly my most favorite data set, not from STIX, that is provided by Solar Orbiter. This is again in EUV. So again, we see something hot. And what we look at here is a very small part of the polar region, the southern polar region. You can see that there is a slight curvature in it, right? So that tells you something about what the radius would be. And so most probably that's 2 floors up would be the center of the other the polar region. And what we see here is, again, first of all, it's not static. Right? This is the movie. It's not real time, but you see it in the corner there. So it's maybe 60 times faster. About a minute is a second. But you see everything changes here. It's also quite nice and not, you should also see it hopefully online, that you see there is field lines that are filled with plasma, and you think, yes, I see how the solar wind leaves there, right? How plasma leaves the sun there. And next to it, you see all these tiny little faint brightenings that are really just a few pixels. And what we think is, this is also part of the solar wind. And I show here a cartoon, what we think it is. So it's magnetic field, right? Some magnetic fields can be that they go out and leave the sun. Of course, magnetic fields need to come back and close up because they're magnetic fields, but nevertheless, on the smaller scales, they leave the sun. Others are just form loops that come out. And those things can, what we call reconnect, which means can regroup to get a different formation. And you can think of that like rubber bands, right? If you twist them up, if you had 2 of these twisted up bands and you reconnect them, you can release that tension. And that's in analog here, what happened. And we think this is really shows that this is a way, of course, also, if I open this loop in A here that is closed and has plasma in it through this form of reconnection, then really that plasma can escape. Right? And so this must contribute to the solar wind. The question is only, is this the major part of it? And so this, my colleagues study this. From STIX is actually a movie that Andrea made in maybe 2 years ago or so. The STIX data is very different. We don't see a million sources like we see in UV because we look only at these times when an eruption happens. And we generally see then emission from really the core of the region where the energy is released, where it gets the hottest. And what we see is this red blobs. This is where it's hottest. This is where the plasma heats up to maybe 20, 30 million degrees. And then occasionally we see these additional bursts of, shown here in blue, this is where electrons that are accelerated in the process, these are electrons that reach up to relativistic energies, how they then slam into the chromosphere. And the diagnostics we have is that we not only make those images, but we also measure the spectrum at the same time. And if you have the spectrum, you can do a fit and get then quantitative results out of it. The low energies in our range shown here in red. The black is the data, and the fit is a thermal fit to it. So we can measure a temperature. We say, how hot is that blob? We can also then estimate how much particles, what's the density in the blob, and what's the energy in this blob. And at higher energies, the spectrum decays, but it doesn't work like a thermal fit. And so this high energy part is described by a power law, and this measures how many electrons are slamming into the chromosphere. And so these are quite good diagnostics because it's quantitative and we can describe the flare energetics with it. And so that's why ESA agreed to have a hard X-ray imager on board solar orbiter. And this is kind of one of our way of we think how this energy is released. It's again a little bit similar as in the other cartoon that I showed, but what it is, if you take a loop and you make it eject out, what you can create is new form. You reconnect the loops here, and this creates then this flare loop. So more or less, what happens next in the flare is this green line that is shown here is reconnecting here and makes a loop that connects back. And in this way, this blob here can escape. And so going back in our picture from before, that's what we observed. And now with orbiter being away from the Earth-Sun line, we can look at this whole thing from two different directions and actually for the first time measure the 3D geometry of this thing, right? Because in all this cartoon, it's always quasi 2D flare thing. If we look at it from one direction, it's always a projection. And so with our Chinese colleagues, they launched about a year and a half ago. We have now a few good events where we can reconstruct this 3D geometry. So this is a scene from Earth. This is the Chinese instrument, and you see these two foot points and the thermal loop, and 20 degrees away from Earth, orbiter sees also these 2 points and the loop. And so now we reconstruct that. And this is actually something we finished yesterday, the first time that we have really measured that loop. And you can imagine to get the 3D effect really makes it easier for us, or actually only possible to truly understand how this magnetic connection actually works. And then my most favorite flares, they look like this. So it's again this simple picture of two locations where electrons slam into the photosphere, the thermal loop. And in this case, we not only see electrons in the chromosphere, but high up. And these are the cases when, for whatever reason, the density in the acceleration region is rather high. And so we have enough collisions to be able to see that. And so we have a few of those cases. And of course, to do within the next year, I hope to get a 3D observation of something like that. And that's where we connect with the theory guys. They try to simulate what's really going on in this region when magnetic field lines reconnect, reform. And so in those, these are maybe a little bit abstract what they show here, but this is what they calculate how magnetic islands in that reconnection region, how they coalesce and how they produce, how they accelerate particles. Just to give an idea that we are also doing physics. This is another example that we recently did. These are simulations, what really happens when electrons hit the chromosphere. And so here you see the distance in the chromosphere. That is just a little bit above the photosphere. And this is where we would expect to see the hard X-rays. This is where the heating actually happens if we put in the observed parameters, and this is at a temperature map. One last fun event. These are events when the flare actually is not happening on the visible part of the disk, but behind, right? Then you don't see the flare, but you see what is ejected, right? And this is one of the very nice cases. Of course, the bigger the flare, the bigger the ejector, the easier to see. And for this, we have STIX observations. And you see here, this is the shock that comes out that you see maybe just flashing out here. And behind the shock, we get a very hot, compact core of the eruption that is thrown out. And it's really a little puzzling how it really happens that that thing gets so hot. And even the spectrum within this hot blob shows still non-thermal particles in it as well. So what's coming up next? The orbiter is going for another 6 years at least. And the next thing is to do a gravity-assisted Venus to get out of the ecliptic. And so with time, the viewing angle will be more and more away from the ecliptic. And this will be very interesting for the EUV and magnetic field measurements to see the polar region. And then, of course, what we try to do since quite a while is say, how can we now use this expertise of STIX, of the detectors, in a CubeSat? And we had at least three proposals that were named, one even twice. The first approach was a mission called MISOLTA, where we said, can we make STIX small enough to fit in a 6 unit? And that was at times when 6 unit was the larger CubeSat, right? Not like these days when apparently 60 units is still a CubeSat. And you see here, that's of course only a sketch, but we have here, I think these were 12. So in this case, we were naive enough to believe we can put 12 of those STIX detectors in a single cube here. You also see how unrealistic these solar panels are. I don't know how we would store them for the launch. So then we did tests. So what we need to do is to make the whole thing fit in a CubeSat is to shrink the STIX optics and make really fine grids. And we didn't really succeed in doing that process. In the US, we had this concept of a 27U, launch compact, and then extend those imaging grids that we need to make images with booms. NASA didn't like that at all. Even we think it's not so crazy as NASA thought it is. But nevertheless, it really showed, I think, for CubeSat, at least in a low budget, an imager is just not feasible, right? And so then we changed the approach with the PADRE concept. That was then funded a year and a half ago and should launch in a year and a half. The other thing is, so it's very clear that for the PADRE, we said no imaging, we just put our detectors in. Great. That's simple, appropriate for a CubeSat. And really, a CubeSat should be simpler than a normal mission. And by making an imager, it's actually more complicated. And that's kind of the wrong approach, right? CubeSat should not be more complicated than. Okay, and so one idea for space weather is just use our STIX detectors with a single simple grid on front, something like this. And a grid like this, you put maybe 10 centimeters above the detector. It makes a unique shadow on the detector, depending where the flare source is. Quite easy to understand. Right? And if you have pixelized detectors at some level, you can reconstruct, okay, if this pixel pattern appears, the source must be over there. Very easy. And that's what we actually use on STIX. Reality is always a little more complicated. Okay, but it works fine. And so what I think can be done easily is use maybe 4 list. If you have more space, 8, then you have more statistics, you see smaller flares. And put over 1 or 2 a grid like this. And then you get a data set of, for each flare, you get time evolution of the spectra, you can measure the temperature, you can measure the non-thermal component, which means the electrons, and you get from where they're coming from. It's not how the image looks, but you can say it comes from that sunspot. And I think that's all what a space weather monitoring mission wants. So that's doable. I gave here some numbers. I gave this kind of presentation maybe 4 or 5 years ago for a mission concept at L5, so the Lagrange point 5, which is 60 degrees away from Earth. And so this is very, very doable for a CubeSat as well. And then with PADRE, we had long discussions what to propose. I said, go simpler, we might succeed. My colleague said, no, we go fancier. Mm-hmm. And they were right, apparently, because we got funded. And so it's a 12-unit CubeSat and 2 instruments in it. You see the big opening, that's the one instrument that's called SHARP. It's a beryllium scatter. And then in the corner, you see an opening with 4 slots, and these are where 4 of those Callis detectors, STIX detectors are in. And it will launch in fall 2025. These are the detectors we're going to use, and I just show it again. The crystal is one square centimeter, and so you see even in STIX they're really close together already. So soldering is not trivial. But this fits, 4 of those fit in a CubeSat in a 1-unit area, right? And this is what we do for PADRE. In one corner, we have this module with 4 of those. Very simple. The only thing that I'm a little, worry is, it's not a worry, but you have to be very careful. You need to have this detector at -20 degrees. And that you do with passive cooling. So these are radiators that connect then to the detectors. And the other instrument is an instrument also working on with X-rays. And you see 8 detectors here. So the inner part are the detectors. So they're grouped around this scattering cylinder. So that means the detectors are really looking not at the sun, but at the scatter. And the X-rays come in and they scatter off the beryllium. And when you measure that and there is polarization, you get a unique signal. And so this is one of those detectors that is back in here. And so we'll see how well this works. Polarization measurements in X-rays are notoriously difficult, or at least people fail. So let's see. And so one thing to say is this PADRE is not a trivial CubeSat. This is already a more complex one. It has a decent budget, right? It's really not subsidized by student labor or by people being paid by different grants. And it is really a lot of work, and it needs few people that really say, okay, I want to do this, I work 100% on it. And all the rest I have to do in the non-existing other percentage besides this 100%. Right? So I know the PI is doing more or less only this. And we have also a system engineer that is really putting a lot in the project manager. So. Yeah, it's a dedication, and we are at the FHNW, we are part of it because it's the STIX detectors and for science, so no hardware involvement. Okay, so this is my my take on this subject of X-ray observation of solar flares and what we could do in CubeSats. I think 2 take-home messages I would be happy if you guys remember is why we do these hard X-rays. It's a key diagnostic to understand the energy release in solar flares. And for a CubeSat, it's really a spectrometer locator it's a good thing to do, I think, because it's high TRL, relatively simple, not too much work, and when we can do it in a 6-unit, I would say for sure.
Okay, thank you, Sam. So time for questions. I think I've seen at least one question online, but if you have a question, you can also either raise your hand and then speak up, or just type your question on the meeting chat.
I think the question was from Adrien, but he's in the room, so Adrien,
Yeah.
you can just ask your question.
In order not to forget, I wonder what's the orbital period of solar orbiter, the elliptical orbit that it's currently in.
Yeah, it's about half a year. So so that means we get 2 close encounters, and they're generally at the moment April and October.
And a follow-up question. So when you are close enough, you can do, I imagine, a lot of science. And when you are really, really far, like at the apohelion, when you do a bit of science still, or?
Yeah, of course, with the flares, we cannot plan those, right? They just happen. And so for me, you know, to see a big flare like today, when we are not super close, is still super interesting, right? Of course, generally, the other instruments that make the images are not on that often. So we might have only every hour an image, which then is, of course, a disadvantage. But we have really a large fleet of spacecraft that look at the sun all the time from Earth, right? And we combine with those. And now with our Chinese colleagues, they have a similar instrument, the STIX. Some things they do better, others not, and so it's perfect to combine. Also with ground-based observatories, the same electrons that we see with STIX, you can also image in radio, because when they fly along the magnetic field lines, they radiate synchrotron image. And so we have very good connections to the radio astronomy community. And that's actually where I did my PhD. So this is very, very much linked. Yeah.
So I see a question in the chat from Lai. What is the value of the attenuator mechanism with respect to the science? Is it working well?
Yes, we have an attenuator in there. For the biggest flares, we will get swarmed with these thermal counts. And so what happens is that an aluminum blade comes in front of the detector and cuts out the low energies. And we have some mechanism to recover some of those, and it really works nicely. And it moves only for the very biggest flares, like this morning it did move. Of course, with the mechanism, you're always worried, right? But this one seems to work quite nicely. Yeah.
What is the mechanism to move? There's a motor, or is it?
Yeah, it's a motor, and so you see here those detectors, right? And they are aligned in these lines, and the space in between those lines. This is where the attenuator sits when it's out, right? And then the attenuator, these are just blades. They move this 1 centimeter over and cover up the detector.
Okay.
The tricky part is it has to be pretty precise, right? There's not so much, and if you don't cover up perfectly, then it's pretty messy, right? So, but it's working well. And this is something we generally need if you wanna, you can design, of course, your instrument by having a very thick entrance window, and then it's always the same, it looks the same like when we insert our attenuator. But then you miss out on all the small flares. So the Chinese instrument, for example, okay, it has also different detectors, but they can survive without an attenuator, but only see the big flares.
So if you were to put these detectors on the CubeSat? Would you be putting an attenuator also, or?
No, we would really avoid that. We would most probably change the entrance window in a way so that we don't need the attenuator. So make the entrance windows a little thicker, and then we can live without having a movable part. I would not feel comfortable at all.
And if you put the grid to improve the location, is it also attenuating the signal? I guess so.
Yeah, the thing is, for some pixel it does, right? And for others it doesn't.
Yeah.
And so you might still run into problems that too many counts come and the electronics cannot handle that, which means then instead of measuring single counts, 2 counts come at the same time, and then it measures with double the energy.
Mm-hmm.
And these are the things that we really have to avoid. And that's why we have an attenuator in STIX.
Okay.
I don't see any other questions in the chat.
Oh, I have a question.
Yeah, go ahead, Martin.
How do you manage the temperature for STIX? Does it have to be at a constant temperature?
Yeah, so there is we have a radiator, or the spacecraft provides a radiator, and we are mechanically connected with that radiator. The radiator gets really cold, and then that mechanical connection is connected to the detectors, or the detector plane that is there mounted, and that makes them cold. And actually, the design now is, as always, one is really conservative in the planning, and ESA is most probably even more conservative than we would be. And so at the end, that radiator is actually too cold. So what happens is that the radiator is every 40 minutes or so has a heater on it and is heated a little bit so that the radiator doesn't get too cool. Which works out nice for us because it means we have rather a very stable temperature. But of course, it's a waste of, we designed our instrument and now using only 8 watts. And I never dare to ask how much power they waste on heating the radiator, right? And, to get a design done with 8 watts is so much riskier than getting a design with 50 watts. And so we have to always balance that. That's for a CubeSat. That's why I said the CubeSat, the thermal design needs to be done carefully, right, to see. And then we have some, we know how these detectors behave, so we can make corrections, but we would need to have a good thermal analysis. Because if it's an orbit with day-night, then it's not so clear how well we can do that. We did now for PADRE some thermal analysis. And it looks okay, but it's just something that needs to be taken care of and understood.
Where is PADRE to be from?
NASA has not told yet what the right share we will get, so we do not know the orbit.
You don't know is that going to change parameters probably?
I think we have a range of parameters, and NASA knows which orbit we prefer. And so it's anything lower, so it should work.
Okay.
Okay, maybe we should make a wrap up, and thanks Sam for his presentation. And stay tuned for next seminars. Thank you, Sam.
Thank you.
Thank you.
Thank you everyone for connecting.